Hello, and welcome back to Physics 41, University Physics 3. So we are still on the last chapter for this course. So far, we have discussed about power in DC, direct current circuits. And the power output of a power supply is just given us the product of the current output and the voltage output. So we will use this concept in dealing with the power in calculating the power in AC circuits. So for this lesson, the third lesson for this chapter, we will be talking about power and resonance in alternating current circuits. So let's first talk about power in resistors. Resistors in AC circuits. So if you have a resistor in AC circuit, the power is basically just the multiplication of the voltage and the instantaneous voltage and instantaneous current. So you will notice that at the maximum, take note in resistors, the voltage and the current phasors are in phase. So they go maximum at the same time, they go zero at the same time, they go minimum at the same time. So meaning at the maximum voltage and maximum current, then that is actually the maximum power, V times I. So V times I, the maximum voltage or the voltage amplitude times the current amplitude, that's actually the maximum power. So the black line here is the multiplication of V and I. And the power is actually always positive because they both have the same sign at the same time. They're both negative. They're both they can be both negative, they can be both positive. So the power is always positive. So you will notice that the power ranges from 0 to a maximum value of V times I. So what is the average of 0 and VI? So it's 1/2 V times I. The middle, that's the average. So half the time it's 0, half the time it's maximum. So the average is in the middle, 1/2 V times I. So V times I here is what we call, V times I is what we call the maximum power. So the average power is just 1/2 the maximum power for resistors in an AC circuit. If we convert this in terms of the root mean squared values, then there will be a factor of square root of 2, a factor of square root of 2, and then, so you will have a factor of 2 times 1/2. So in terms of RMS values, the average power is just VRMS times IRMS. That is for resistors. Now, in the case of pure inductors and pure capacitors, the average power is actually 0. Because if you multiply the voltage, instantaneous voltage and the instantaneous current, this is the power curve. So the black lines are the power curves. And you will notice that half the time it's positive and half the time it's negative. The same is true for capacitors in AC circuits. Half the time it's positive, half the time it's negative. So just look at the black curve because that is the power curves. So therefore, the average is 0. So the average power of an inductor, average power delivered, or the average power loss in an inductor is 0, and similar for a capacitor. Now, if you have, if the three circuit elements are present, the resistor, capacitor, and inductor, so we call that a general alternating current circuit, then the average power is just 1/2 VI, which is the power for average power for a resistor, cosine phi. So take note that the phase angle, if you have a pure resistor, is 0. So cosine 0 is 1. So you have for the resistor. And the phase angle for inductor and capacitor are 90 and negative 90 degrees. So cosine of 90 or cosine of negative 90 is 0. So you get 0 power. But in general, phi is not 0 if the three elements are present. So actually, if I'm not mistaken, if you have a general LRC circuit, the phase angle is actually the tangent inverse of the inductance, inductive capacitance minus the inductive reactance minus the capacitive reactance over the resistance R. So this is the phi in general. So the cosine of phi, the cosine of the phase angle, the angle between the voltage and the current phasors, is actually what we call the power factor, because VI, that's basically, or VRMS, IRMS, that's power due to the resistor. So cosine of phi, that's what we call the power factor. Okay, so another important phenomenon involving LRC circuits is resonance. So this happens when you tune an LRC circuit, and one application is radio receivers, AM and FM. So as we have discussed in the previous chapter, you can actually tune or modulate the current amplitude or the frequency of the current oscillation of the current. So frequency of the current oscillation or the amplitude of the current. So take note, an alternating current looks like a wave. This is the amplitude, and basically the distance from the crest to crest is the lambda, the wavelength, and the wavelength is related to frequency. So you can change the wavelength or the frequency, or you can adjust the amplitude. So that's the two ways to modulate the LRC circuit, tuning circuit in a radio. So when resonance is achieved in a radio, the current amplitude becomes maximum. So when the receiver circuit is tuned to a particular frequency, hence the term resonance. So you have discussed about resonance when you discussed discuss about waves in mechanics. So basically standing waves. So in this case, you create standing current curves or standing current waves, which becomes a constructive interference of waves, making the amplitude higher. So this frequency, wherein the resonance, of course, is what we call the resonance angular frequency, and this happens when the reactances, inductive and capacitive reactances, are the same. And so we can solve for the resonance angular frequency, 1 over square root of LC. And again, if only the frequency is given, this is equal to 2 pi times the frequency, F naught. So omega naught is the resonance angular frequency, F naught is the resonance frequency. Okay. So let's now have some examples for this chapter. So let's first have an example for power. So you have an electric hair dryer. It's rated at 1,500 watts at 120 volts. So this power here, 1,500 watts, this is the average power. 120 volts, this is the VRMS, the root mean squared voltage. So you are asked to calculate the resistance of the dryer, the RMS current, and the maximum instantaneous power. So assume the dryer is a pure resistor. So if you assume the dryer as a pure resistor, then the average power of a resistor is just VRMS over IRMS. So take note, for a resistor in an AC circuit, uh, Vrms is just equal to Irms over times R. Now, we want the current is unknown. Irms is unknown. The only given is the power, average power, and Vrms, and we are asked to solve for R. So we need to eliminate I. So we can actually write I as Vrms over R. We substitute that here, so V over R, so that we can have the average power as Vrms squared over R. And we can now solve for R. R is just equal to Vrms squared over the average power. So you will have 120 volts squared divided by 1500 watts, and you will get 9.6 ohms. So that is the resistance of our hair dryer. Now for letter B, what is the RMS current? So this is the formula. IRMS current, IRMS for letter B is just VRMS over R. But actually, you can also use this. Average power over V. You can also use this equation. So the same result, average power over VRMS. So these two equations will give you the same result. It will give you a value of 12.5 amperes. Okay. The last question is, what is the maximum instantaneous power? So the maximum instantaneous power, that's actually V times I, the voltage amplitude, the maximum voltage times the maximum current. But take note, the average power is actually 1/2 V times I. Therefore, V times I is actually twice the average power. So therefore, the maximum power is twice the average power. In this case, the average power is 1500, so the maximum power is 3000 watts. So this means that for this hair dryer, even though it's rated at 1500 watts, the power is actually swinging from 0 to 3000 watts. So 0 to 3000 watts, having an average of, in the middle, 1500 watts. Okay. So this is the summary of our results. So for the second example, we are trying to solve the power in an LRC series circuit. This is actually just very simple because we didn't discuss the LRC series circuit very thoroughly. So suppose in this LRC series circuit, the voltage from the source is 50 volts. And the phase angle between the voltage phasor and the current phasor is 53 degrees. And the current is, instantaneous current is 0.10 amperes. Sorry, this should be the current amplitude. This is not the instantaneous current, but the current amplitude. This should be capital I. So this should be I. So the current amplitude is 0.10 amperes. So calculate the power factor and the average power delivered to the entire circuit. So the power factor is just cosine of the phase angles. In this case, 53 degrees, and you will get 0.60. For the average power in this general LRC circuit, it's just 1/2 the voltage amplitude, the current amplitude. So this is the voltage amplitude of our source, 50 volts. This is the current amplitude output, 0.10 amperes. This is the maximum current and the maximum voltage. Cosine P, the power factor. So you have 50 volts. This is 0.10 amperes. This is 0.60. And this will give you an average power of 1.5 watts. So this is the power delivered by this alternating source to the entire LRC series circuit. So this is the summary of our results. So for the last example, for this lesson, let's have tuning a radio. So in a radio, there is an LRC series circuit. So don't mind these terms here. These are actually the results. These are actually the values. This one. So this just indicates voltmeters and ammeters, and these values are actually RMS values. Okay. So the circuit is just actually a very simple one. You have an alternating voltage source connected to a resistor, an inductor, and a capacitor. So this square here is just our circuit. So you are asked to find, or the voltage of the source, the voltage, the VRMS, the RMS voltage of the source is actually 1 volt. So take note, the ammeters and voltmeters only read RMS values. You need to multiply by square root of 2 if you want to get the voltage amplitude or the current amplitudes. So 1 volts, RMS voltage of 1 volts. So find the resonance frequency for this LRC circuit configuration, and at the resonance frequency, you find the inductive and capacitive reactance and the impedance. And you are asked to find the RMS current. So this is a series circuit, so there will be a current flowing through the circuit. So it's actually an instantaneous current. So one time it's in this direction, and another time it's in this direction, the opposite direction. It's continuously changing directions. I'm just gonna put 2 arrows there. But you are asked to find only the RMS current, root mean squared current, and find the RMS voltage across each element. Take note, there's only, since this is a series circuit, there's only one value of RMS current flowing through the 3, but each of these 3 have different voltages. So okay, so these are actually the answers. So we'll try to obtain these answers. Okay, for letter A, find the resonance frequency for this LRC circuit. So the resonance frequency, again, is just given by the angular frequency. Resonance frequency is 1 over square root of LC. So L is given by 0.40 microhenry. That's 0.40 times 10 to the negative 3 Henry. And the capacitance is 100 picofarad. Pico is times 10 to the negative 12. So you substitute those values here, and you will obtain a value of 5 times 10 to the 6 radians per second. But we are asked to find the resonance frequency, not the angular frequency. So we need to equate this to 2 pi times the resonance frequency. So to solve for the resonance frequency, it's just 5 times 10 to the 6 radians per second over 2 pi. So in this case, we need to drop the radians unit. We need to drop this. We drop that unit. So the unit that will be left will be actually the unit of 2 pi is actually radians. So that one. So the unit of pi is actually in terms of radians. So you can think of it as canceling each other out. So the final unit is 1 over second or hertz. And you will get 800,000 hertz or 800 kilohertz. This is actually in the AM region, AM band, lower AM band frequencies. Okay, so that's for letter A, 800 kilohertz. For letter B, at this frequency, 800 kilohertz, what is, at this frequency, 800 kilohertz, or at this angular frequency, 5 times 10 to the 6 radians per second, what are the reactances, inductive and capacitive reactances? So for XL, we just use omega naught times L. So omega naught is 5 times 10 to the 6 radians per second. L is this one, 0.40 times 10 to the negative 3 Henry. You multiply that, and you will get a value of 2,000 ohms. For the capacitive reactance, it's 1 over omega naught C. So C, the capacitance is 100 picofarad, 100 times 10 to the negative 12. So you multiply that, 1 over that one, of course, you will still get 2000 ohms, because that is the condition for resonance, that the reactance, inductive reactance, and the capacitive reactance must be the same. So they're both 2000 ohms. Okay. So how about for the impedance? So to solve for the impedance Z, just the square root of R squared plus XL minus XC squared. But since XL and XC are the same, so XL minus X, this is 0. So this is basically 0. So meaning the impedance is just square root of R squared or R, where R is equal to 500 ohms. So this is the impedance. The impedance is equal to R, where R is equal to 500 ohms. That is for letter B. Okay. Let's now go to letter C, the RMS current. So to solve for the RMS current, since we already know the impedance, we can now solve for the RMS current. It's just the voltage amplitude, or VRMS, root mean squared voltage of the whole circuit, which is 1 volt, over the impedance. In this case, the impedance is equal to the resistance, 500 ohms. So 1 volt over 500 ohms, that will give you a value of 2 times 10 to the negative 3, or 2 milliamperes. That is the IRMS. So for letter D, the voltages across each of these, so VRMS is just IRMS times the resistance. So across the resistor, the voltage is just IRMS times R. So you will get a value of 2 milliamperes times 500 ohms. You will get a value of 1 volt. And for the VLRMS across the inductor, it's actually IRMS times XL. So 2 milliamperes times XL is, we actually have obtained 2000 ohms. So you will get 4 volts. And since XL and XC are the same, then this is also equal to the RMS voltage across the capacitor here. It's actually equal to, also equal to 4 volts. Okay. But since since the inductor, the voltage in the inductor and in the capacitor are actually out of phase, they're when we say out of phase, they're actually exactly opposite of each other. When one voltage is positive, the other voltage is negative. So when one voltage is positive 4 volts, the other is actually negative 4 volts. So at any given time, the total voltage drop across these two elements are actually 0 volts, because they are out of phase. So you will notice that the total 1 volt VRMS is just due to the resistor, 1 volt. Okay. So as a summary of the results, this is the resonance frequency for this circuit. And the reactances are both equal to 2000 ohms. The impedance is just equal to the resistance, 500 ohms. The RMS current is 2 milliamperes. And these are the voltage across each of the circuit elements. So that's the end of this lesson. So this is actually the second to the last topic for this chapter. And for our last chapter, we will be discussing about transformers.